Breast milk science. It's a thing. And it's our thing. We're ByHeart. We're an infant formula company on a mission to get a lot closer to the most super food on the planet, breast milk. Our patented protein blend has more of the important and most abundant proteins found in breast milk. We're the first and only U.S.-made formula to use organic, grass-fed whole milk, not skim. We make our formula in our own factories in Iowa, Oregon, and Pennsylvania, using a small batch manufacturing process that works to preserve the integrity of our ingredients. We ran the largest clinical trial by a new infant formula company in 25 years and clinically proved benefits like easier digestion, less gas, and softer poops versus a leading infant formula. We were the first infant formula company to earn the Clean Label Project Purity Award. And while we've put a lot into ByHeart, there's a long list of things you won't see on our ingredient list, like no corn syrup, no maltodextrin, no GMO ingredients, no soy, no palm oil. ByHeart, a better formula for formula. Learn more at byheart.com.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime, Series 22, Episode 81, for broadcast on the 6th of November, 2019. Coming up on SpaceTime, a method called quantum squeezing, which can detect every stellar mass black hole merger in the universe, a mission to slam an impactor into an asteroid, and the US Air Force's X-37B space shuttle returns to Earth following a record-breaking 780 days in orbit. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have found a way to detect virtually every stellar mass black hole collision in the universe by refining a technique called quantum squeezing. Until now, many signals have been drowned out on laser interferometer gravitational wave detectors by so-called quantum noise on the laser light pushing the mirrors of the laser interferometer around, making the measurements fuzzy or imprecise. But a report in the journal Nature Photonics claims scientists have now refined a method called quantum squeezing to dampen or cancel out this quantum noise, improving the sensitivity of the detectors by making measurements more precise. Stellar mass black holes are formed out of the gravitational collapse of stars far more massive than our Sun. When these stars run out of fuel, the opposing forces, the balancing act between nuclear fusion and gravity ceases, and gravity wins, causing the star to implode, rebounding in a titanic explosion, a supernova, capable of briefly outshining an entire galaxy. What's usually left is a superdense stellar remnant called a neutron star. But occasionally the stellar collapse is so great it exceeds the limit of a neutron star, crashing all the way down to create a black hole, an object of infinite density in zero volume. When two black holes collide, they trigger some of the most violent events in the universe, creating gravitational waves rippling through space-time. These ripples cause the very fabric of space-time to stretch and contract by less than the diameter of a photon. And that's where LIGO, the Laser Interferometer Gravitational Wave Detectors in Washington State and Louisiana, come in. Each LIGO observatory fires lasers into a beam splitter, which then shoots the beams along two perpendicular 4-kilometer-long tubes equipped with mirrors at the far ends. The reflected laser lights then sent back to the detector where, theoretically, they should recombine. But when a gravitational wave passes through the detector, local spacetime, including the two beamlines' reflected lasers, are stretched and compressed ever so slightly, leaving them out of phase, the signature of a gravitational wave event. Using multiple gravitational wave detectors allows scientists to determine the direction of the wave source. The addition of a third detector called Virgo, located in northern Italy, has further improved detection. A fourth observatory in Japan will be the first to be built underground and is expected to come online later this year. And a fifth gravitational wave detector, originally offered to Australia but rejected by the then Gillard Labor government, is now being built in India. The LIGO detectors are so sensitive that just the random quantum variability in the number of photons can disturb the mirrors enough to mask the wave-induced motion. One of the scientists behind the new quantum squeezing research, Dr. Robert Ward from the Australian National University, says the breakthrough will be crucial for the next generation of gravitational wave detectors, which are expected to come online within the next 20 years. Further experiments are now being prepared to confirm the team's proof of concept. LIGO and Virgo have detected numerous black hole collisions, as well as the collisions of two neutron stars and possibly also a black hole eating a neutron star. The current generation of quantum squeezers developed by the Australian National University, together with other ANU upgrades at the current LIGO detectors, have already provided dramatic improvements to their sensing capabilities. And this new research proves that scientists can cancel out other quantum noise that can affect the sensitivity of the detectors. In fact, Ward says the new generation of LIGO detectors will have the capability to detect virtually every black hole smash in the universe at any given moment. The LIGO team plans to design and build the upgraded quantum squeezers within the next few years. Ward says the new devices will then be retrofitted to the current detectors, enabling scientists to detect many more violent events much further into the universe.
Squeezing is a word that we use when we talk about manipulating quantum noise. And so that leads to a second thing of what is
quantum
noise. Yes. Yeah. And it's this idea that when you take a measurement of any quantum system, you can't do it with an infinite amount of precision. So there's always a little bit of fuzziness. And this is not true in all cases, but in many cases it is. And in particular, it's true with anytime you're measuring light or laser light. And this fuzziness has a particular form where there are these two characteristics of quantum system. And those could be, in terms of laser light, those two characteristics are things we call the amplitude and the phase. But it might be more familiar to think of a particle's position and its momentum. So you've heard of Heisenberg's uncertainty principle.
Especially when you're being picked up by a cop and the cop says, do you know what you were doing? And can tell you either where I am or what I was doing, but not both.
That's exactly it. So I can tell you where I am or what I was doing or how fast I was going, but not both. And what we do in that case, there's a certain minimum where you take the product of those two things, where you are and what you're doing, you multiply them together, and that has to be greater than Planck's constant, where Planck's constant is this number that kind of defines when things become quantum mechanical or not. So when you multiply those things together, you cannot go lower than a certain bound. So you can't measure both things at the same time with infinite precision. And what we do when we squeeze is we say that what that product means of multiplying those things together has to be less than a certain amount. It's like we kind of write those two things, we manipulate their units, so it looks like a little area where if I multiply my uncertainty in my position with my uncertainty in my momentum, I get an area, and I would write my units so that area is like a little circle. And so that area now is the minimum imposed by quantum mechanics, and ordinarily it's a circle. But if I reduce my uncertainty in one thing, so I can tell you exactly where I am, or I can tell you really well where I am, but can't tell you my momentum anymore. Now you can imagine that circle is being pushed down. The uncertainty circle is being pushed down so that it's very narrow in the position and very wide in the momentum. It's become an ellipse. It's not a circle anymore. Mm-hmm. And so the circle has been squeezed, because this is what happens when you squeeze an orange. Say you cut an orange in half, and it's a circle, and then you squeeze it, and it becomes an ellipse. It gets narrower in one dimension and broader in the other dimension. So that's why we call it squeezing, is just this analogy with oranges or geometry or lemons.
Okay. I was thinking that this is all caused by virtual particles or virtual particle pairs popping in and out of existence all the time. That's not the problem?
That is related. That is definitely related. And in quantum mechanics, we have this wave-particle duality. And we talk about light as a wave, and we talk about light as a particle, and then we say, oh, no, it's really both. But when you're solving a problem, often you need to stick with one of those things. It is both things, but the math for the two things is different. So you choose one or you choose the other. And this idea of virtual particles popping in and out of existence is just one of those formalisms. So it is that. It is exactly that, but it's also these other things that I've been talking about. And it's just which mathematical tool you use to attack the problem also kind of defines the way you think and talk about it.
So by squeezing, it allows you to, more precisely define the fact that you've just had a gravitational wave pass through the detector.
That's right. Yeah. So that fuzziness, the gravitational wave, what we do when it comes into the detector is we go through all of this trouble to make the detector, the masses in the detector very quiet so that they can respond to a gravitational wave, and that's the main thing that they're responding to. But then we also have to measure the mass or measure the position of the test mass in our detector, of the test particle that is responding to the gravitational wave. And we measure that position with light. And that light is quantum mechanical. And so the quantum noise on the light then limits our ability to measure the gravitational waves. And by doing this squeezing, we can overcome that limitation. So the test particle is actually the test mass. And these are our 40 kilogram super pure cylinders of glass, the purest glass. And we attach mirrors to the test mass. And sometimes people use these words interchangeably. But what it really is there's a hunk of glass, which is kept very still by all of our sophisticated vibration isolation system. And we attach a mirror to that. And it's that hunk of glass that is interacting with the gravitational wave. And then we shine a laser beam on the mirror that's attached to that hunk of glass, and we detect that laser beam after it bounces off. And we have 4 of these hunks of glass, and the laser beam interacts with them in different ways, and then they're recombined at the beam splitter, and we detect that interference pattern. But all of that interference is just a trick to let us measure the positions of those hunks of glass.
These are the glasses at the far ends of the, you said there were 4, so there'd be what? At both ends of the tunnels?
At both ends of the tunnels, that's right.
You've used this method before, the squeezing method, and now you've improved it.
So now what we've done is we've demonstrated something different about the squeezing. So the squeezing, that quantum noise from the light happens in 2 different places. So up to now, we send our light onto our test mass, and it bounces off. And then we measure it. And because the light is quantum mechanical, that measurement of the light when it comes back to us is a little bit random. And that's that quantum fuzziness. And so we've squeezed that part of the light when it's coming back by adding another field that we call squeezed vacuum on top of the light coming back after it's already interacted with our test mass. So that's got a long history, and that's installed in the gravitational wave detectors in the U.S. now. It was installed last year, and the gravitational wave detectors have been operating with that squeezing now. But there's another step, which is that when we send the light in to get to the test mass, when it bounces off the test mass, there's also a little bit of randomness there. And that randomness is slightly different. And because the light has its own momentum, each time a particle of light hits the test mass, it gives it a little kick. And so now what we've done, if we shine enough light on the test mass, is we've taken the quantum noise of the light, and we're actually moving the thing we want to measure just by the act of measuring it. So this is a quite different situation, whereas before, the quantum noise was just our ability to measure the light. Now the quantum noise is the light we're putting on is actually disturbing the system we are trying to measure. And what we've done with this test, with this work, is we've shown that we can now quantum engineer the light we are using to measure the system to reduce that disturbance.
How do you do that?
It's squeezing again. It's a slightly different form of squeezing, but now we're squeezing the light that we send into the apparatus to measure.
That's Dr. Robert Ward from the Australian National University. And this is SpaceTime. I'm Stuart Gary. Astronomers studying an ancient quasar have discovered a primitive gas cloud, providing new clues about the birth of the universe's first stars. A report in the Astrophysical Journal claims the ancient cloud has a surprisingly modern chemical composition, and that suggests that the first stars must have formed very soon after the Big Bang, 13.82 billion years ago. You see, these molecular gas and dust clouds are the nurseries where stars are born. They contain information about an early phase of galaxy and star formation, a sort of snapshot taken just 850 million years after the Big Bang. This cloud was found serendipitously during observations of a distant quasar, catalogued as P183 plus 05, and it has the properties expected to be found in the precursors of modern-day dwarf galaxies. When astronomers look at distant objects, they're also looking back in time. And this gas cloud is so distant that its light has taken nearly 13 billion years to reach the Earth, meaning what the astronomers are now seeing is what the gas cloud looked like nearly 13 billion years ago. The study's lead author, Eduardo Bernardos from the Max Planck Institute, says this is an extremely interesting epoch. You see, within the first 100 million years after the Big Bang, the first stars and the first galaxies formed, but the details of that complex evolution are still largely unknown. So this very distant gas cloud was a fortuitous discovery. Bernardos and colleagues were following up on several quasars from a survey of 15 of the most distant quasars known when they noticed that P183 plus 05 had a rather unusual spectrum. When Bernardos analysed a more detailed spectrum obtained with the Magellan telescopes in Chile, he recognised that there was something else going on. The weird spectral features he saw were traces of a gas cloud very close to the distant quasar. And that made it one of the most distant gas clouds astronomers have yet been able to identify. Quasars are extremely bright active galactic nuclei generated by supermassive black holes. Matter swirling around a black hole, before it's gobbled up and disappears forever, is heated up to enormous temperatures reaching hundreds of thousands of degrees, in the process giving off huge amounts of radiation. And this has allowed the astronomers to use the quasars as background light sources to detect hydrogen and other elements in absorption. If a gas cloud is directly between the observer and a distant quasar, some of the quasar's light will be absorbed. Astronomers can detect this absorption by studying the quasar spectrum, that is, the rainbow-like decomposition of the quasar's light into different wavelengths. This absorption pattern or spectra contains information about the gas cloud's chemical composition, its temperature, its density, and even about the cloud's distance. You see, each chemical element has a specific fingerprint of spectral lines, narrow wavelengths in which atoms and molecules can emit or absorb light especially well. So the presence of a characteristic fingerprint reveals the presence and abundance of a specific chemical element or molecule. Also from the spectrum of this gas cloud, the authors could tell the distance to the cloud, and that they were looking back into the first billion years of cosmic history. They also found traces of several chemical elements, including carbon, oxygen, iron, and magnesium. However, the amount of these elements was tiny, just 1/800th the abundance in the atmosphere of our Sun. Astronomers call all elements heavier than hydrogen and helium metals, and this measurement makes this gas cloud one of the most metal-poor and distant systems in the known universe. The team then began looking to see if this system could still retain chemical signatures produced by the very first generations of stars. Finding these first-generation, so-called population 3 stars is one of the most important goals in reconstructing the history of the universe. In the later universe, chemical elements heavier than hydrogen play an important role in letting gas clouds collapse to form stars. But those chemical elements, notably carbon, are themselves produced in stars and are then flung into space in supernova explosions when those stars die. And that's the dilemma. For the very first stars in the universe, those chemical facilitators simply wouldn't have been there, since directly after the Big Bang there was pretty much only hydrogen and helium atoms with just a pinch of lithium and beryllium. And that's what makes these first stars, these population 3 stars, so fundamentally different from all later stars. But the analysis shows that this cloud's chemical makeup was not chemically primitive, but instead surprisingly similar to chemical abundances observed in today's intergalactic gas clouds. The fact that this cloud in the very early universe already contains metals with modern chemical abundances poses key challenges for the formation of the first generation of stars. In fact, the study implies that the formation of the first stars in this gas cloud system must have begun much earlier, as the chemical yields expected from the first stars had already been erased by the explosions of at least one more generation of stars. The authors say that a particular time constraint comes from Type 1a supernovae, cosmic explosions that would be required to produce metals with the observed relative abundances. And the problem is, such supernovae typically need about 1 billion years to happen, which puts a serious constraint on any scenarios of how the first stars formed. Now that astronomers have found this very early cloud, they're systematically looking across the sky for additional examples. You're listening to SpaceTime. Still to come, the United States Air Force's X-37B space shuttle has returned to Earth following a record-breaking 780 days in orbit. And later in the science report, could disease lie behind religious beliefs in good and evil? All that and more still to come on SpaceTime. NASA and the European Space Agency are planning a double mission to slam an impactor into a pyramid-sized moon orbiting a mountain-sized near-Earth asteroid. The primary asteroid, called Didymos, is some 780 meters in diameter. It's orbited at a distance of around 1.2 kilometers by a small 160-meter wide moon called Didymoon, which will be the target of the impactor. The idea of an asteroid with a small moon orbiting it isn't new. Around 15% of asteroids are believed to be part of double or triple asteroid systems. Didymos has been selected because it'll come within 11 million kilometers of the Earth in 2022. That's comparatively close by astronomical standards. And this will provide NASA and the European Space Agency ESA with an opportunity for a planetary defense experiment. For NASA's part, it'll slam an impactor called DART into Didymoon in 2022 to see what happens. The collision is expected to cause Didymoon's orbital velocity to be shifted by around 0.5 millimeter per second, changing its rotational period enough to be measured with Earth-based telescopes. At the same time, DART's collision is expected to leave a 20-meter wide crater on Didymoon's surface, and mapping the shape of this crater will provide unique information for the design of future asteroid deflection missions. It'll also shed light on the asteroid's surface properties and internal structure. Astronomers want to know if Didymoon's a monolithic mass or simply a rubble pile, loosely held together by gravity. They also want to know if it's composed of large or tiny grains, and if its subsurface composition is the same as its surface. And that's where ESA's contribution, the Hera spacecraft, comes in. Hera, named after the Greek goddess of marriage, is slated to launch in 2024, arriving at the Didymos system in 2026. It'll investigate the aftermath of the impact of NASA's DART spacecraft, undertaking detailed follow-up observations surveying the impact site. The joint agency mission will provide scientists with data on whether a kinetic deflection technique could work to shift the orbit of an asteroid on a trajectory targeting the Earth. Hera will also gather crucial scientific data on asteroids as a whole by carefully studying the exterior and interior properties of both Didymos and Didymoon. Hera will map Didymoon's surface down to a resolution of just a few meters, and the area around the DART impact crater down to less than 10 centimeters in resolution through a series of close flybys. It'll also map much of the surface of the primary asteroid Didymos, providing crucial scientific data from 2 asteroids on a single mission. Because Didymoon is in such a close orbit around Didymos, the change in its orbit will be easy to observe from the ground, compared to performing a comparable test on an individual asteroid. A full picture of the collision and the resulting momentum transfer will only become possible once Hera maps the mass of Didymoon to a high level of certainty, which is necessary for scientists' models of the tiny two-body system. Hera will also deploy 2 briefcase-sized 6-unit CubeSats, which will perform the first ever multi-point measurements of an asteroid pair. The first CubeSat, called the Asteroid Prospection Explorer or APEX, will perform detailed spectral measurements of both asteroid surfaces, measuring the sunlight reflected by Didymos and breaking down its various colors to discover how these asteroids have interacted with the space environment. The other CubeSat, called Juventus, will measure the gravitational field as well as the internal structure of Didymoon, and eventually it'll land on the tiny moon's surface. It'll also line up with Hera to perform satellite-to-satellite radio science experiments, and carry out a low-frequency radar survey of the asteroid to unveil its interior. This report for ESA TV by astrophysicist and former Queen lead guitarist Brian May.
Hera is going to show us things no one's ever seen before. This ESA mission will be humanity's first ever spacecraft to visit a double asteroid, Didymos. This asteroid is typical of the thousands that pose an impact risk to our planet. Imagine a mountain in the sky with another rock about the size of the Great Pyramid swinging around it. That's Didymos. And just the seemingly tiny moon would be big enough to destroy a city if it were to collide with the Earth. But we're going to find out if it's possible to deflect it. This is going to be really, really hard. Aiming at a 160-meter wide target across millions of kilometers of void. Could we stop an asteroid hitting planet Earth? The dinosaurs couldn't, but we humans have the benefit of knowledge and science on our side. Hera is led by a multinational team of scientists and engineers, humanity's makers and doers. Right now, all we have is many years of research and theories, but Hera will revolutionize our understanding of asteroids and how to protect ourselves from them. First, NASA will slam its DART spacecraft into the smaller asteroid at more than 6 kilometers a second. Then ESA comes in. Hera will map the impact crater left by DART and measure the asteroid's mass. Knowing this mass is key to determining what's inside and knowing for certain whether we would be able to deflect it. Next come our briefcase-sized CubeSats. If you think of Hera like an aeroplane, then CubeSats will operate more like drones, able to take more risks, flying closer to the asteroid, carrying state-of-the-art science instruments, eventually touching down. The scale of this experiment is huge. One day these results could be crucial for saving our planet. Hera's up-close observations after DART's impact will help prove whether asteroids can be deflected, prove whether this is an effective planetary defense technique, so that if an asteroid ever poses a real threat to Earth, we'll be ready.
That's astrophysicist and former Queen lead guitarist Brian May ending that report from ESA TV. And this is SpaceTime. Still to come, we'll look at the dark and deadly side of so-called healing crystals. A United States Air Force X-37B space shuttle has returned to Earth after a record-breaking 780 days in orbit. The delta-wing spaceplane returned to the ground heralded by a crack of double sonic booms as it swooped in for a perfect touchdown, landing on NASA's Space Shuttle runway at the Cape Canaveral Air Force Base in Florida. The more than 2-year OTV-5 mission hosted several classified payloads, as well as providing a ride to orbit to a number of small satellites. There's plenty of speculation about what the X-37B does while it's up there, including suggestions it's serving as a spy satellite and monitoring the activities of other satellites. Previous missions have tested new types of drive and sensor systems. The only payload the Air Force was willing to confirm was the Air Force Research Laboratory's second Advanced Structurally Embedded Thermal Spreader, ASSETS-2, which measured the long-term performance of an oscillating heat pipe in orbit. The next X-37B mission is now slated for early 2020, launching on an Atlas V rocket from Cape Canaveral. The X-37 was originally designed as part of a NASA project. The robotic reusable wing spaceplane would be launched from inside the payload bays of NASA's space shuttles and then released to undertake their own missions. These would include the deployment of satellites from their own payload bays, as well as the rendezvous and repair or modification of satellites in orbit, or even the capture of orbiting satellites for return to Earth. However, following the 2003 Columbia disaster, the X-37B was modified to launch from Delta II rockets instead. It was then formally transferred from NASA to the US Air Force in 2004, and the project became classified. We know it carried out a series of glide tests using the Scaled Composites White Knight mothership, and in 2006 the Air Force announced that it would proceed with a variant of the original NASA X-37 to be called the X-37B. Because of concerns over the unshrouded spacecraft's aerodynamic properties during launch, the new X-37B variant was designed to fit inside a payload fairing. Boeing built 2 spacecraft for the Air Force, simply designated as X-37B Orbital Test Vehicles 1 and 2. One of the X-37B's most annoying features, at least for the enemy, is its ability to radically change its orbit. For example, it can fly in a highly elongated orbit that dips down into the upper atmosphere, and then use its wings and atmospheric drag, as well as its maneuvering thrusters, to dramatically change its orbit midstream so it doesn't fly on a predictive schedule. This annoying ability to suddenly disappear means that when the Russians and Chinese track the spaceplane and guide their own satellites to try and get a better look at what it's up to, US mission managers simply change its orbit so that nothing shows up where the enemy expects, forcing Moscow or Beijing to then try and reacquire the spacecraft and start the operation all over again. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study warns that paracetamol use during pregnancy may be linked to an increased risk of childhood attention deficit hyperactivity disorder, or ADHD, and even autism spectrum disorder. Scientists made the call after examining umbilical cord blood samples for traces of paracetamol and finding increased risk of ADHD and autism in children where the drug was present. You can read the study in full in the Journal of the American Medical Association. A new study suggests that disease could lie behind religious beliefs in good and evil. The findings, reported in the Proceedings of the Royal Society B, are based on investigations into the beliefs of 3,140 people from 28 countries. Researchers found that high levels of disease were associated with stronger beliefs in the devil, the malevolent power of the evil eye, and in witches who channel evil. They also found conservative ideologies more prevalent in countries with high disease burdens. The authors suggest these beliefs may be causing people to behave in ways that help avoid the spread of the disease, such as shunning the afflicted, who they believe may be possessed with the forces of evil, which may be an effective way of avoiding the spread of infection in countries where the risk of contracting an illness is high. New research warns that global warming may increase the risk of undernutrition through the effects of heat exposure on people. Scientists reached their conclusions after analysing daily hospitalisation data for nearly 80% of the population of Brazil between the year 2000 and 2015, and looking to see if there was a link between daily temperatures and hospitalisation for undernutrition. The findings, reported in the journal PLOS ONE, showed that for every 1 degree Celsius increase in average daily temperature, there was a corresponding 2.5% increase in undernutrition hospitalizations, with people under 19 and over 80 at highest risk. Overall, researchers estimated that heat exposure was responsible for 15.6% of undernutrition hospitalizations during the study period. In what could be a major game-changer for the electric car, scientists have developed a battery that could theoretically provide a range of at least 320 kilometres after just 10 minutes on a charger. For a regular lithium battery to charge this quickly would take in so much energy, it would risk a condition called lithium plating, a buildup of metal around the anode of the battery severely deteriorating its life. But a report in the journal Joule claims researchers discovered they could get over the lithium plating issue by charging the battery to an elevated temperature of 60 degrees Celsius and then letting it discharge at cooler temperatures. Researchers say they're now working towards getting this process down to 5 minutes. Dinosaur footprints in Alaska suggest that one of the most common dinos of the Cretaceous era seemed to prefer to chill out at the beach. Paleontologists reporting in the journal PLOS ONE claim they've found an abundance of footprints from duck-billed hadrosaur dinosaurs in what were then tidal areas. And the evidence suggests these herbivores weren't alone. The authors also found footprints from armored dinosaurs called ankylosaurs, a few birds, and even the Alaskan version of the tyrannosaur. The authors say their findings show that hadrosaurs were incredibly abundant in their day, and in some ways could be likened to today's caribou, which, when you think about it, inhabit the same region 67 million years later. A new study has found an evil and deadly dark side to the growing demand among the New Age woke for so-called healing crystals. These pretty-looking stones have become a billion-dollar industry. However, Tim Mendham from Australian Skeptics says they're usually mined in deadly conditions in some of the world's poorest countries.
Yeah, you go into any sort of New Age shop or, mind, body, spirit trade fairs, that sort of stuff, and you'll find crystals everywhere. And the trouble is crystals have to come from a place, and they tend to come from underground in caves and that sort of thing, and from places where people dig them up. And what they don't think about is the market for these things is huge, and the market for it's a multi-billion-dollar market is the market for crystals. And the crystals suppliers have to find them from someplace. Big sources are India, China, Brazil, and Madagascar. They're the main producers of crystals. And the trouble is these are often sort of cottage industries to trying to dig them up, where the whole family and the kids included are digging down to try and find crystals in very unsafe conditions. And of course there are some classic cases which are sort of wonderful crystal formations in the ground which are just being pillaged and destroyed. As you can imagine, anyone going in there with their pickaxe and sort of just tearing this stuff out is not going to have a lot of subtlety in the way they do it. I've known geologists who have told me personally that when they find a good site, they will bury it to stop the new ages of people coming down and trying to dig it up for their crystal healing purposes and that sort of stuff. I mean, there's nothing in crystal healing powers of crystals that is in any way substantiated by science. There is nothing there at all. I mean, they're pretty looking things, they're nice on your shelf, etc. But as for any sort of practical purposes outside of the piezoelectric effect, which is not something you can do in your own hands, but any healing effect and that sort of thing, any medical effect is just totally unsubstantiated. And the thing is, you are destroying sites and you are tapping into third world countries and abusing the individuals there who would go for these dangerous practices of digging this stuff up.
A lot of kids die
money.
digging these things up, don't they?
They do. I mean, it's a serious thing. You've got to think of where they come from, and they don't just appear out of thin air. Someone somewhere, and it's often sort of poor families and kids, etc., are digging them up, their own danger, for you Westerners to have a nice little thing on your shelf and to also pretend that you're curing someone's illness.
Yeah, these aren't big open-cut mines we're talking about. These are tiny little crevices dug into the ground, barely wider than the little boy or little girl who's being forced to go down there, and they can be 20, 30 metres deep, and there's no support for them, so they often collapse. Consequently, often the child doing the digging is killed.
That's right. That's exactly right. I mean, this is the dark secret, if you like, of crystals, and it's a very sad situation.
That's Tim Mindham from Australian Skeptics. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcasts, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web that I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram. On Facebook, just go to www.facebook.com/SpaceTimeWithStuartGary, and you can also find us on the SpaceTime with Stuart Gary YouTube channel. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.